In the name of God, hello dear students, welcome back to Ferkhwa's website. My name is Masoud, I'm a physics teacher. Actually, so far we explained 20 questions from chapter review. Right now, we are going to answer question 21. Let me read the question for you. Question 21, explain why Earth is not spherical in shape and why it bulges at the equator. So we have this, there's this, the shape of Earth. I told you in previous lectures, in previous lessons, that the Earth is not perfect circle. It's not perfect actually circular shape. It looks like an orange. It bulges at the center. It bulges at the equator. It sticks out at the equator. That's why, let's say it says, this is the question, why is Earth, let's say, not spherical in shape and why it bulges at the equator? Let me read the, let's say, answer for you. And in previous lessons, I explained it for you. And let me read the answer for you. It says, because gravity that acts as centripetal force is not enough to overcome inertia of equatorial regions. So I told you there's a competition between two things, between two factors. There's a competition between centripetal force and inertia. If centripetal force overcomes the inertia, so the object remains in its circular track. If inertia overcomes the centripetal force, actually the object tends to move, let's say, tangent to the circular track. In this situation, over a billion of years, actually, over a billion of years, equator bulges at, let's say, equatorial regions, bulges, I can say, bulge, or equatorial regions, I can say bulge and stick out because of the Earth rotation, because inertia of these regions overcome the gravitational force, which act as a centripetal force. That's why inertia of the equatorial region overcomes the gravitational force. That's it. Question 21. Because of Earth rotation, you would weigh slightly less at the equator than you would at the poles. Explain. When a person, let's say, goes to the equatorial regions, for example, the person goes to Brazil of any country located in this line, actually. In this situation, the person weighs less compared to the same person, let's say, goes to the poles, actually. Why? Because let me read the question of teacher's book, and I have, let's say, my explanation for this, let's say, phenomenon. Let me read it. At the equator, there is a part, this is the answer of teacher's book. At the equator, there's a part of centripetal force. There's a part of centripetal force, Fc, that makes you remain on circular track. It's a part of centripetal force. So, not the entire centripetal force, let's say, act on the object, because in the equatorial regions, this is my explanation. In the equatorial regions, Earth has a longer radius than in the poles. So let's say these regions, or equator, let's say, moves away from the center of Earth compared to the poles region. That's why in this situation, the larger the radius is, the less the weight is, based on the equation of general gravitational law of Newton. Let me read the equation, and I'm sure you know the equation. It's very famous. Yeah, I just focused on the weight and the radius of Earth. The larger the radius is, I mean in the equator, the less the gravitational forces. That's it. This is my explanation. It's beneficial for better understanding the, let's say, the phenomenon. Question 21, why does mud fly off a rapidly turning wheel? Why does mud fly off, let's say, fly off a turning wheel, right? The mud's internal cohesion is not able to provide enough centripetal force. It means, you see, it means inertia of the mud overcomes the, let's say, cohesion force. So the concept is the same. The concept of the, let's say, question 21, right? And question 23 is the same. In question 21, we said that the inertia of equator overcomes the gravitational force of Earth. Here we say, in question 23, inertia of mud overcomes the cohesional force of cohesion. That's why, let's say, I can say it ejects from the tire, from the circular track. So this is the question number 23. Let me read the question 24. And after that, let's say, we complete our solutions or explanation. Question 24. Astronauts floating around inside the space shuttle are not actually in a zero gravity environment. So astronauts within the spacecraft or space shuttle are not in a zero gravity environment. What's the real reason astronauts seem weightless? Why do astronauts seem weightless, right? So this is the explanation, answer of teacher's book. The astronauts, number one, shuttle, number two, and the objects and the object stuffs within the shuttle are all in a free fall, because the shuttle itself, before, let's say, every other object, I can say shuttle is in free fall, and anything within the shuttle is in free fall as well. That's why they have the same acceleration, and the acceleration is gravitational, let's say, or free fall acceleration, or acceleration due to gravity. That's why they seem, let's say, weightless. And I have my explanation here, but I didn't mention it. Let me tell you, let's say, orally. In this situation, why do, for example, astronauts seem weightless or seem weightless? Because there is no normal force over there, right? In an outer space, there is no normal force, and the normal force, let's say, makes the object feel heavier, right? Normal force, let's say, is the reason of let's say, weight, right? Here on the surface of Earth, why do we feel, for example, that we have weight actually? Why do we feel heavy on Earth actually? We say, let's say, we feel that we are not light, we have a, let's say, weight, because of normal force. Acceleration due to gravity, or I can say gravitational force, let's say, moves the object down. It pulls us, let's say, down the Earth, right? And simultaneously, normal force stands against the gravitational force. That's why you feel that you have a weight. You feel that you are heavy, right? But in outer space, or even, let's say, if you do a simple experiment, if you, let's say, tie a, let's say, chair If you tie yourself on a chair, right? If you fasten, for example, rope about your waist and you tie to the chair. In this situation, and you fall off the building. In this situation, you feel weightless. You feel like astronauts in the space shuttle. Why? Because there's no, let's say, normal force. No normal force acts on the legs of a chair, right? To balance the gravitational force. That's why you feel weightless. But here in our textbook, it doesn't mention this phenomenon, this concept, and just says that because the astronauts and objects within the shuttle are all in free fall acceleration, are all in free fall, and they pick up, let's say, acceleration due to gravity or G. Question 25. A girl at a state fair swings a ball in a vertical circle at the end of a string. Is the force applied by the string greater than the weight of the ball at the bottom of the ball's path? I'm sure you are familiar with this question. This is a question of national exam, but in multiple choice. Not like this, actually, not like this. So what's the reason? At the bottom, I told you this, let's say, this note at the bottom of the circular track, right? Let me draw it. At the bottom here, I can say Ft overcomes the weight of the ball. Force of tension is greater than the gravitational force. That's why it says, why, let me read the question again for you. A girl at the state fair swings a ball in a vertical circle at the end of the string, right? Is the force applied by the string? I mean, tension force. Is the force applied by the string? Means Ft. It focuses on Ft. Is Ft greater than the weight of the ball at the bottom? Yes. At the bottom, Ft is greater than Fg. That's it. Because at the bottom of the path, Ft, force of tension or tension force, is equal to the summation of gravitational force and centripetal force. Here, Ft is greatest. Let's move on to question 26. Next question, question 26. It's a problem, right? We have to solve it. Let me read the question for you. A roller coaster car speeds down a hill past point A, this is point A, and then rolls up a hill past point B. So the car reaches here, it passes over the A and it reaches B, and it, let's say, exceeds B after that. It says, as shown in figure below, we have the path. This is a roller coaster path, actually. The car has a speed of 20 meters per second. What's this information? It's tangential velocity, Vt, right? At the point A. So we have Vt here. At point A, we have Vt. Vt is present, 20 meters per second, especially at this position at the bottom of the path. If the resultant force on the car is, what's this information? Resultant force means centripetal force. Let me write it with another color. So Fc. Fc is equal to 2.06 times 10 to the 4 Newton at this point. So we have two information here. Fc and Vt are present here, right? And it's directed toward the center. It's clear, you know, the information of the Fc actually toward the center, like this. This is Fc, right? So it says, what's the mass of the car? We look for the mass of car. We have to summarize the information within the question. Vt is present. Fc is equal to this number. R is equal to 10 meters. Take it from the figure. R, you have to take it out from the figure. R is equal to 10 meters, and we look for M. So which rule is convenient? This rule. Teacher, what's this rule? This is the rearranging of the force of, let's say, centripetal force, Fc is equal to m Vt squared over r. If you rearrange this equation for m, you can get this form of the equation, which is Rfc divided by Vt squared. Just multiply the numbers, the figures actually, and find the mass of the car, right? R is equal to 10 meters. Fc, this number, 2.06 times 10 to the 4, divided by Vt 20 squared. And this is the, let's say, mass of the car. This is the answer of A. Part B, it says, what's the maximum speed of the car? So here we look for tangential velocity. What's the maximum speed? We look for Vt of the car, right? We look for Vt. Let me read it like this. So we look for Vt of the car can have at point B. So we look for tangential velocity at point B, at this position. We want to, actually we need tangential velocity of the car at this position exactly. For the gravitational, we have a condition here. For the gravitational force, only to hold it on the track. What does it mean? For the gravitational force, only to hold it on the track. Means only gravitational force, let's say, is a centripetal force. Let me translate it into the mathematical form. So what's the mathematical form of this condition? Gravitational force holds it on the track. It means gravitational force is in charge of keeping the object in a circular track, or in other words, I can say Fg is equal to Fc, right? Fg is equal to Fc. If you obey this condition, you can find the answer, let's say, quickly. And this is a condition, it's very important. That's why I underlined the condition for you. This is the main part of the question, actually. Given an unknown, m is equal to 15, let's say 515 kilogram. We've solved that, we found that, let's say, already in part A. R is equal to 15 meters. Actually, be careful. Don't, let's say, don't use 10 meter, because right now the car is in another, let's say, circular track. It's in a bigger circular track. Actually, that has a greater radius. The radius of the second circular track is 15 meters, it's not 10 meters. And we look for tangential velocity. But I told you, you have to focus on the condition. I explained it for you. Fc is equal to Fg. So Fc, write the value of Fc. Right? Write the value of Fc. Let's say Fc is equal to mvt squared over r, and Fg is equal to mg. Right? So here, teacher, can I cancel out, for example, mass with mass? Yes. Mass is cancelled out from both sides of the equation because it's repeated, actually. So we look for Vt, cross multiply the fraction to get this form of equation. Vt is equal to radical Rg. Sure, why do you put radical? Because Vt is squared, and you have to put the, let's say, the rule under the square root. So Vt is equal to radical R. I told you, be careful not to use the first radius. You have to use the second, let's say, radius, which is 15 meters multiplied by 9.81. And this is the answer, 20.1 meter per second. Let's move on to question 27. Let me read the question 27 for you. Find the average angular speed of Earth about the Sun in radians per second. So this question is a question of national exam. And I wrote the national exam options for you after the solution. From here, this is the answer of this is the question of our textbook, right? But actually, in national exam, you know that the questions national exam are all in multiple choices. That's why I mentioned the multiple choice of national exam after this solution. Let's discuss the question. It says, find the average angular velocity. So what do we look for? Average angular velocity. Angular speed or velocity means omega average. So we look for omega average of Earth about the sun in radians per second. You have to find omega average in rad per second. We have a hint here, note. Earth orbits the sun once every 365.25 days. This is the duration of 1 year in days, actually. How much is the duration of 1 year in days? 365.25, let's say days, exactly. Let's say by this duration, by this time interval, Earth, let's say, completes one revolution. And we say this, let's say we are, and we call this revolution a year, right? We say 1 year is, let's say, past. That's why this is the question. We look for omega. So you have to, let's say, you have to take out some information from the question itself. You have to visualize the situation during a one complete, let's say, cycle of, let's say, circling about the sun. In this situation, so we say that 1 year is past, right? 1 year is past. In this situation, 1 year means one revolution. Delta theta is present. Delta theta is equal to one revolution, right? One revolution. And what do you say about delta t? Delta t is given. It says 365.25. So delta t is given as well, 365.25 days. Two things are available. Delta theta, but delta theta in rev. One revolution is equivalent to 2 pi radian. Just divide delta theta by delta t, that's it. And this is the answer. So delta theta becomes 2 pi in radians divided by delta t. But here, 365, I forgot to, let's say, to use the 0.25. You have to use the exact number because this is the given of question. 365.25 multiplied by, so this is in time interval in days. Is time interval in days, let's say, valid in SI? Is it accepted in SI? No. You have to convert day into the second. How do you convert day into the second? So each day contains 24 hours. That's why you have to multiply this number, 365.25 by 24. Are we done? Did we convert the day to second? No. We just convert the days into the hours. We have one or two more, we have two more steps. After that, 24 hour, how many, let's say, minutes are there in 24 hours? 60 minutes. Are we done? No. We have one more step because you have to convert the hour into the, let's say, minute into the second. Or you can, let's say, memorize this number. 1 hour contains 3,600 seconds, right? 1 hour contains, let's say, 3,600 seconds. That's why, let's say, after 24, you can multiply 24 by this number, 3,600, to convert the hour into the second directly. If you divide this number, you can find this value 1.99 times 10 to the negative 7 rad per second. So I want you to find the correct answer here. A, 7.1 times 10 to the negative 4, it's wrong. B, 1.99 times 10 to the power negative 5, negative 7, it's true. So B is true. C, it's very far from this value, and let's say D as well. So the answer is B. It's very easy, right? It's nothing. You have to, let's say, imagine. You have to visualize the situation. You know that in 1 year, actually, Earth, let's say, circles the sun, and the revolution is equal to 1 rev, or 1 cycle is equal to 1 revolution. You have to convert the revolution into the rad just by multiplying by 2 pi. After that, this revolution is taking place, let's say, during 365.25 days, but this time interval is not accepted in SI. You have to convert it by second. How do you convert this number by second, right? How to convert it into the second? Just multiply the number of days by 24 and 300, let's say, or 3,600 to find the answer. Guys, this is the answer of this question. Let's move on to another question. Question 28. The top within a washer goes into its spin cycle starting from rest. So it says starting from rest. You have to summarize the information. Let me underline it for you. It says starting from rest. It means omega initial is equal to 0, starting from rest, reaching an angular speed of 11 pi rad per second in 8 seconds. So what's this? This is omega final, and this is time interval, delta t, right? At this point, the lid is open. The lid of the, let's say, washing machine is open, and the safety switch turns off the washer. Right? So it starts, let's say, stopping actually. It says the top slows to rest in 12 seconds. So the top of washing machine stops in 12 seconds. It says it comes to rest. It stops eventually. What does it mean? It means omega, let's say omega final for the final case actually. Omega final for the switching off is equal to 0. At last, the washing machine is stopped, right? So you have to separate the situation into 2 parts, right? You have to. There are 2 solutions for solving this problem. I solve the problem normally, and after that, I'll tell you a fast way, right? Right now, I just solve it, let's say, normally. So it says the top slows to rest in 12 seconds, right? Through how many revolutions does the top turn? So we look for what? We look for the, let's say, delta theta in rev. So I told you have to separate this situation into 2 parts. We have a starting case, and stopping case. A starting case means the top starts from 0, right? It starts from rest, and that's how omega I becomes 0. It speeds up to this number, 11 pi rad per second. That's the omega f. So this situation is, let's say, going on till 8 seconds. After that, let's say another case, let's say, is started, right? But here right now, I solved the delta theta for this case as if there's no another case. So this question is 2 in 1, 2 questions in 1 question. Firstly, I want you to focus on the starting case only, as if there is no stopping case, right? Separate the case as I told you. So in this situation, I find delta theta number 1 by means of this information. Delta theta number 1 is equal to 1 over 2 omega I plus omega f multiplied by delta t. This is one of the kinematic equation. Delta theta 1 is equal to 1 over 2, 0, omega initial 0, omega final is 11 pi, multiplied by 8 is equal to 45 pi rad. So let's say we solve the starting case. Leave this case. Let's move on to another case, which is stopping case, as if, let's say, there's no starting case. Focus on this one, right? Let me explain it for you. In this case, actually, so we have a stopping case. In the case of a stopping, let me tell you a note here. Omega I for the stopping case becomes omega f of the starting case, or in other words, I can say omega f final angular speed for the starting case becomes omega I for the stopping case, right? Why do we say this? Because it reaches this value from the beginning, and it reaches this value. After you switch off, actually, you turn the machine off. In this situation, it slows down from this value. That's why omega f for the starting case becomes omega initial for the stopping case, because it slows down from this value. That's why it becomes omega initial for the stopping case. Teachers, what do you say about the final omega or final angular speed? Final angular speed is equal to 0 because it says the machine at last stops. Eventually, it stops actually, but time interval is different. During 12 seconds, the machine is stopped. So in this situation, you have to find another delta theta. I numbered as delta theta number 2. We have to use the same rule, 1 over 2 omega I plus omega delta t. Omega delta theta number 2 is equal to 1 over 2 omega I for the stopping case, 11 pi plus omega f final angular speed becomes 0, multiplied by 12, and the answer will be 66 pi rad. Right now, are we done? No. You have to, let's say, you have to add the angular speeds up together. After that, convert it to the revolution. So what's the delta theta total? Means delta theta for the starting case plus delta theta for the stopping case. Means delta theta 1 plus delta theta 2, which is equal to 44 pi plus 64 pi, 66 pi becomes 110 pi rad. This is delta theta total. But question says, what's the revolution? How many revolutions does the top turn during, let's say, during its motion, right? That's why it's not our answer. You have to divide this value by 2 pi in order to convert the value into the rev. That's why 110 pi divided by 2 pi is equal to 55 rev. Here I can say pi simplifies with pi, and 110 divided by 2 becomes 55 rev. This is the scientific way or normal way to reach the answer, right? But there's a fast way, but fast way here is not scientific. Sometimes fast way works actually for finding the answer, but it's not scientific. Sometimes works and it's scientific. But here, let me mention this. It's not scientific. Physics doesn't believe this actually. It's the fast way and it's not scientific, but you can get the answer in a very short time interval. It saves actually, it saves time for you, especially for the for you that actually you need, let's say you need to save time for 50 question in a national exam. That's why it works here, actually. It works, but it's not scientific. Firstly, I want you to, this is the fast way. I want you to, let's say, add the time interval together. There were 2 time intervals for the washing machine, 8 seconds for the starting case, 12 seconds for the stopping case. So add them up together, and the answer will be 20 seconds, right? Delta theta total. Only one time use this rule here. Only once use it, actually. 1/2, let's say 0 plus 11 pi multiplied by 20, right? So the answer will be 100 pi, 100 pi, 110 pi, right? 110 pi, right? Delta theta total becomes, so this number, I want you to divide this value by, I want you to divide this value by 2 pi, and you get the same answer of the, let's say, of this previous solution. You can find the answer, no problem, and it's fast way, but it's not scientific, because here you have to use the rule twice, right? But here only you use the rule, let's say, once, actually. In this situation, 0, let's say, for omega initial or for omega final, it doesn't matter. Whether you use 0 for the omega initial or final, it doesn't matter, because this approach actually works only for the case that either the initial case is 0 or final case is 0, right? Initial angular speed is 0 or final angular speed is 0. If there were, let's say, if initial angular speed were not 0, if final angular speed were not 0, so you would not, let's say, you are not allowed to use this rule. So this rule only works for the case of, for example, 0 initial omega or 0 final omega. That's it. This is the question, question 28. Guys, I'm gonna finish the lesson here. Thank you very much for watching this video, and bye-bye.